Solve the inequality. All right, so in these problems, we have rational inequalities. For rational inequalities, we basically do the same thing we did for the polynomials. We set them equal to 0. So we're going to go ahead and say 3x plus 2 over x minus 3 is equal to 0. And then we try to determine the zeros of the function, and one other important thing, which is where the rational expression is undefined. So let's start with the zeros. The only way a fraction is equal to 0 is if its numerator is equal to 0. So we want to go ahead and set 3x plus 2 equal to 0 to figure out where the overall fraction or rational expression would be equal to 0. Well, if we subtract 2 from both sides, we'll end up having 3x is equal to negative 2. Then you divide by 3, and you get the idea that x is equal to negative 2/3. That's going to be our 0 for the function. Now, we also have to figure out that if x minus 3 is equal to 0, that would make the denominator equal to 0, and so we set the denominator equal to 0 to see where the function is undefined. So basically, when you're working with rational expressions, you set the numerator and the denominator equal to 0 and solve. The parts that make the denominator equal to 0 will be parts that we have to be careful about because we want to make sure that we don't include those in our solution set, because those numbers will make the function undefined, right? So, or make the rational expression undefined. So we'll end up solving this and show that x is equal to 3 gives you a 0 in the denominator, hence it makes an undefined point on the number line, right? So let's go ahead and plot these on a number line. Negative 2/3 would be on the left and 3 would be on the right, correct? And then what we're going to do is test points like we did before. So I'm going to test something to the left of negative 2/3. How about we test negative 1, right? Between these two, we might want to test 0. That's a nice, easy number to test. And then we could probably test something like 4, right? Positive 4. All right, let's run the test by plugging it into the original inequality and see if it works. So if I have negative 1, I'll have 3 times negative 1, which is going to end up giving me negative 3 plus 2 over negative 1 minus 3. Is that less than or equal to 0? Well, what you're going to end up getting is basically negative 1 over negative 4, and that gives you a positive fraction actually, right? So negative 1 on top, then you'll have negative 4 on the bottom, but that's the same as saying 1/4, and 1/4 is not less than or equal to 0. So that does not work. So we'll say this is false. All right, let's look at testing 0 itself though. All right, if we want to test 0, we'll plug 0 into the inequality. We'll have 3 times 0 plus 2 over 0 minus 3. That's going to give you basically 2 over negative 3, which is negative 2/3. That is less than or equal to 0, so that actually works, right? So we're going to say this part of the number line does contain solutions. Now, the thing we want to be careful about now is we have an equality symbol here, right? So we have less than or equal to 0, and we know that negative 2/3 makes the fraction equal to 0, or the rational expression equal to 0. So we want to actually include that answer by putting a square bracket around it to show we're going to include that. We do not want to include 3. We never want to include 3 because that makes the function undefined. So we would certainly be rounding this here. It has to be rounded because we don't want to include 3. Let's test 4 though to see if 4, or the region that includes 4, is part of the solution. All right, so let's do that. We'll have 3 times 4 plus 2 over 4 minus 3. Well, that would give you 3 times 4, 12, plus 2 is 14, over 4 minus 3 is 1. That's 14. Is that less than or equal to 0? No, that'd be false, right? That's not true. So basically, the answer for this problem is from negative 2/3 up to 3, those set of values, but we want to include negative 2/3 and not include 3. And again, it's important that we don't include 3 because remember where 3 came from. That was the value that made the fraction undefined. So we want to not forget to make it rounded always for that number. All right, that's the answer for A. Let's look at B then. For B, it's already basically set equal to 0. We just need to change the inequality to an equal sign, and then we're going to go ahead and do the same thing we did before. We're going to go ahead and set the numerator and the denominator equal to 0 separately, right? So let's talk about the numerator first. If I have x plus 5 quantity squared equal to 0, that's the same as saying I have x plus 5 times itself, right? Equal to 0, and of course that means x plus 5 must be equal to 0, right? So in other words, x must be equal to negative 5, right? Okay, so we just basically separated them and set them equal to 0 separately. I didn't write the second one because obviously we get the same solution from both, right? All right, there it is. I've written the second one, even though I said I wasn't going to. There it is. All right, so that's the place where we get a 0 in the function. How about where the function is undefined? To do that, we need to set the denominator equal to 0. If we do that, we get x squared minus 9 factoring into a difference of two squares type factoring, right? So x squared minus 9 is a difference of two squares. We break that up as x, and then 3, and then 3, and then a sign of each, plus and minus. So separating these two and setting them equal to 0 separately, we get x plus 3 equals to 0, and x minus 3 is equal to 0. And finally, when we solve, we get that x is equal to negative 3, or that x is equal to 3. These are two places where the function would actually be undefined, where the rational expression would be undefined. Remember what we do with those? We have to put them on the number line just like we do with the other values, and then we have to test. So let's put them on a number line. So we have negative 5 is the first number that we'd come across. Then we'd have negative 3, and then positive 3. And let's go ahead and test. Let's go ahead and test a number to the left of negative 5. So for example, we might test negative 6, for example. A number between negative 5 and 3, let's go ahead and test negative 4, right? Nice and easy. Between negative 3 and 3, we like to test 0. That's the simplest one usually. And then after 3, we might test something like positive 4. All right, let's go ahead and plug these numbers into our original inequality. Remember what our original inequality said. It was basically x plus 5 squared on top, so it'd be negative 6 plus 5 squared on top over x squared, or in this case, negative 6 squared minus 9. I want to see if that's greater than or equal to 0, right? Is that true, greater than or equal to 0? All right, well, let's work that out a little bit. Negative 6 plus 5 is just negative 1, but when you square it, it becomes 1, and that will be over 36 minus 9. Now, 36 minus 9, of course, is going to be 27. 1 over 27 is positive. It's greater than or equal to 0. So this would be a true region. It would be greater than or equal to 0 here. Remember that the negative 5 came from setting the numerator equal to 0, so we're actually going to include that as an answer because that'll make it equal to 0. So I'm going to use a square bracket there to indicate we include negative 5 in that part of the number line. All right, let's test negative 4 now. If I want to test negative 4, I do the same thing. I say negative 4 plus 5 quantity squared over negative 4 squared minus 9. And then we're asking, is that greater than or equal to 0? Because that's what our original inequality said, right? Greater than or equal to 0. All right, well, negative 4 plus 5 is positive 1, and you square it, you get 1. And then on the bottom here, you have 16 minus 9, essentially, right? Because negative 4 squared is 16. 16 minus 9 is 7. And so we end up with another positive answer. So we include that in our solution, right? But we cannot include the negative 3 because the negative 3 here, you'll notice that negative 3 came from setting the denominator equal to 0. Remember, any point that was found by setting the denominator equal to 0 cannot be included in your solution set because those points cause the rational expression to become undefined. Okay, so we can actually remove that square bracket we put around the negative 5 because it looks like that we are going to include all of this area, right? So obviously we'll include the negative 5 with the region that's to the left of negative 3. Let's go ahead and test 0 then. If we test 0 in the rational expression, we end up having 0 plus 5 quantity squared over 0 squared minus 9. And then 0 squared is 0, and then you have minus 9. That's going to give you 25 over negative 9, which is less than 0, not greater than or equal to 0, right? So in other words, it doesn't pass the test, so we'll say false here, right? Because we're supposed to have numbers that are strictly greater than or equal to 0, and negative 25 over 9 is less than 0. Okay, let's test the last area, which is the area that involves numbers greater than 3. Okay, so we'll plug in 4 as a test point, right? So we'll have 4 plus 5 quantity squared over 4 squared minus 9, and we're looking for this to be greater than or equal to 0. Well, certainly 4 plus 5 is 9, squared is 81, and then we have 16 minus 9, which is 7, and 81 over 7 is greater than or equal to 0, so that passes the test. So we're going to include all these numbers. We need to make sure that we round the bracket here on 3, because again, that came from setting the denominator equal to 0, which means that 3 will give us an undefined point. Okay, that means our final answer will be from negative infinity, right, up until we get to negative 3, round the brackets there for both of them, so that means we're not including negative 3. Then we union, or we pick up from positive 3 and go all the way up to positive infinity. That's the region of the number line that contains the solutions to the inequality that we have above. And that's it.